Oh, here is a mute button. I found it. Okay, so we will have a bit of a delay, something like 1-2 seconds delay between what I say and what you will see on the screen. I will try to adjust the way I speak appropriately, but as you can imagine, this will be a bit weird, and I apologize for that. I wasn't able to find a way to fix all the Zoom issues. For some reason, Zoom has delay for me, no matter which device I use. So yeah, but as I was told, it's better this way than no way at all. So we will speak about CAN extensions, mainly following Emily Reel's book, Categorical Homotopy Theory. Yeah, that's how it's called. It's the first chapter of the book. I guess we are interested in it because we will later speak probably about derived functors, and derived functors can be expressed as some CAN extensions, but nonetheless, CAN extensions is such a general thing and such a nice concept that it's useful to know it regardless. So let's move on to the math concepts. Imagine that we have a diagram like you see here on the screen. Well, there is some functor and there is another functor k, and we would like to extend in some sense the functor f to the category D. Well, generally speaking, of course, you cannot extend it. Also, by the way, I don't see the chat, so if there is something to say, I need people to have courage to unmute themselves or to tell me how I can see the chat. Or actually, I can see it on that device, so it should be fine. So what I was saying is that we cannot extend the functor f to the category D. Obviously, like we might have some arrow in C go into some arrow in E. And I mean, there might be just no arrows in E, for example, and there will be some, okay. Anyway, like with functions, we cannot extend functions. Clearly, if something is not injective, then something is not injective. It's not necessarily extendable, but we can approximate our extension and to express extension via some universal property, and this is what CAN extensions are about. So let's write the definition. So the left CAN extension of f along k is, first of all, a map from D to E, and secondly, a natural transformation with a universal property. The universal property says that if you have some other map like this, so if you have another potential, sorry, let's see that you close the window. If you have another potential extension G, So I say that for any G and for any natural transformation from G composed with K, from F to G composed with K, so for any G and any, let's say, eta, and here I should also denote this natural transformation somehow. Let's go with new. These factors, this whole construction of factors through the connect tension. So this diagram becomes our definition, our construction of the connect extension. Plus whiskering of K with some map, with some natural transformation. So for any G and natural transformation from F to G composed with K, we have some natural transformation from the connect extension to G, such that this triangle is decomposed as this composition of these natural transformations. And you can just write it by adjunction because, well, it basically says that you have a junction between functors, because what it says is that if you have a map in the functor category from C to E, from F to G composed with K, then this is the same as the map from D to E from left connect extension of F along K to G. So on the left we have this one, and on the right we have this arrow. This lets us rewrite the definition, maybe not rewrite, but yeah, rewrite the universal property of left connect extension as left connect extension along the functor K is left adjoint to precomposition with K. Cool. Any questions so far? Okay. Yeah, and what I wanted to say about extensions that if you have non-trivial arrow here and no non-trivial arrows in D, then of course there's just no map here. Like if you have some non-trivial arrow here coming to non-trivial arrow here, and there are no non-trivial arrows in D, then there are no non-trivial arrows in E to be obtained from any functor from D, so there is no strict extension, obviously. All right, so there's also the notion of the right connect extension, which is the same thing, but the directions of arrows are different. It's also a map from D to E. But now we have a functor from its composition with K, sorry, natural transformation from its composition with K to F. And the universal property is, of course, that every other map, every other triangle like that factors. So if we have some other picture like this, we have G and we have a natural transformation from G to G composed with K to F. And then it necessarily factors through our right extension. So right extension is right adjoint. We expect to map into it. So this becomes our G. There is factorization like that. And of course, the adjunction here is that if you have a map from G composed with K to F inside the functor category e to the power of C, then this is the same as having a map from G to the right can extension of F along K inside the functor category e to the power of D. Cool. So one standard example here, and probably the best way to think about the concept is, the concept and example is the induction and co-induction. Recall that if you have two groups, well, if you have in general a group, you can form its D-looping, which is a groupoid with one object and the set of arrows, the group G. This means that if we have two groups, H inside G, then we have a map of their D-loopings. Which means that we can restrict maps to some other categories. In particular, what is a vector space? Well, okay, vector space is just a vector space. What is the presentation on G on some vector space? This is functor from BG. So G vector space is a functor from BG to the category of vector spaces. All right, so this means that we can compose with our inclusion of the loopings, and this way to X we can assign the restriction of X, which is just the same vector space but with H acting on it by first including into G and then applying G action. And so we get a diagram of this form. We have BG, so we have G vector spaces, probably. We have G vector spaces, we have H vector spaces. We can pass from G vector spaces to H vector spaces by restricting, and turns out that there are two ways to pass back. And since restricting is precisely the restricting along some functor, adjoints here are going to be precisely left and right can extensions. So if we denote this by I. Then this is left extension along I, and this is the right CAN extension along I. And the first is also known as induction, and the right one is known as co-induction. So another example, assume that we are working with simplicial sets. Then we can, for the simplicial category, so delta is simplicial category. So it's basically finite ordinals. Finite non-zero ordinals, where its subcategory consisting only of ordinals up to n, and it defines an inclusion of categories. And whenever we see inclusion, we expect to see some CAN extensions. And indeed, if you have a simplicial set, X, then you can restrict it along this inclusion. So if you have simplicial set, you have its restriction. And so you can hope to pass back by CAN extension. We get the diagram like we had before with vector spaces. We have simplicial set. Restricting to this simplicial set subscript n, and we have two CAN extensions. We have not really proven yet that CAN extensions exist, but assuming they do exist, we have two things like that. So on the top we have left CAN extension along this inclusion I. On the bottom we got the right CAN extension. So we get this wonderful diagram. So we can go from simplicial sets back to simplicial sets in two different ways. So we get this co-monad on top, which is called Q, and the monad on the bottom is called cos-Q. And of course, these are like skeletal and co-skeletal functors. To convince you that this is how you really can get skeletal and co-skeletal functors, assume that you have a map in simplicial set from say co-skeleton of y to x. Then by junction, this is the same as map from restricting n to y to restricting n to x, right? Because this is like composition of two left adjoins. This is like sorry, from skeletal y, because this is one composed with restriction. And this in turn is the same as a map from y to co-skeleton of x. Now, it is quite logical that a map from skeleton and skeleton of y to x is the same as just map of the restrictions on n. And also, you have this equality of this with the map from y to co-skeleton of x. And another definition you might have seen is that x is co-skeletal. Maybe we should say n co-skeletal if mapping to x is the same as mapping from n skeleton. So map from y to x is the same as a map from n skeleton of y to x. Like the nerf of a category is co-skeletal, for example. And well, this is precisely what we have here, because if co-skeleton of x equals x, then we get precisely this definition. And so finally, I guess the last piece of this puzzle to convince you that this is indeed skeleton and co-skeleton would be to show that SQ is indeed giving you the skeleton. And I hope we will be in time to show this later when we learn how to compute the CAN extensions. And by the way, let's move on to computing CAN extensions to formulas, how to really obtain them in co-complete categories. If there are no questions so far. All right. So first of all, let's define ends and coends. So assume we have some functor h, and it's basically a bifunctor. It's contravariant in one coordinate and covariant in another. Then we can produce as an integral for the coend. Is that it equalizes, it co-equalizes all the maps of this form. So assume that we have h of c prime c, and assume that we have some map from c to c prime. So we should say for all maps c to c prime, we can pass from this mixed valued h to h of two letters, which are the same. So from h of c prime c, we can pass to h of c c, or to h of c prime. And what the coend does is it equalizes all these arrows. So this has to commute, and the coend is the universal thing with this property which can be expressed by saying that H is a co-equalizer. Sorry, not H, but the integral of H is a co-equalizer, well, of clearly the diagram which runs over all arrows. And to each arrow, well, maps the corresponding H in two different ways. I mean, to each arrow in one way, of course. So here there are two obvious maps, which are actually just drawn above this there, and the co-equalizer of these two things is called the coend, and of course the end is the same thing, but you take equalizer instead of co-equalizer. Yeah. So for example, if suppose that we have two functors, say suppose that we have a pre-sheaf from category C, and a co-pre-sheaf on the same category. Then we can form. Then we can take the product. We can take the product, and then the coend of C is what can be thought of as the tensor product of F and B. Because what the equalizer tells us is basically that we have to take all pairs F, G, and we should equalize them according to with respect to the relation like F times phi G equals F phi G. Here phi is an arrow from here, and this is phi, so here we would have something like F inside capital F of C prime and G inside capital G of C. And so we could either pull F along C, or we could push G forward along phi, and the result of these two things has to be the same, but well, this is just the standard tensor product relation. So in particular, inspired by the fact that for our modules, we of course have R as the tensor product unit. We can also claim that any functor G is actually any functor value of any functor G on some T is nothing but its tensor product with the uneta of C. Well, indeed, because if we have as dense product with Ioneda, what we have is some arrows phi, g, and the equalizing property here tells us that this is precisely the same as identity arrow and phi g. And of course, we can just map this into phi g, and this will be the inverse for the map which sends g to, say, g prime, so that we don't have clash of notations, g prime to 1 g prime. So we get two maps here which are obviously inverses. This way you get this funny form of Koyaneda lemma saying that to take the value of a function is the same as to tensor it with the representable, which is represented by the value which we are taking, and the object which we are taking the value of or on. So yeah, another example is that if we have two functors f and g from C to D, then we can form the end of the set of morphism between them. So in our case, H is equal to D of to D applied to maps between F and G. And this is nothing but natural transformations between F and G. Well, indeed, what the universal property of the N tells us is that if we have a map from C to C prime, and if we have the corresponding arrows, then the composition has to be equal in our end. But this is precisely the definition of the natural transformation, because it says that if we have, yes, it says that if we have like a map from f of C prime to G of C prime and f of C to G of C. So we start from have map from f of C prime to G of C. And there are two ways to get sorry, I wrote all the arrows in the wrong direction. This is why it makes no sense whatsoever. Because this is the end, not the co-end. Okay, now that makes more sense. So if we want to get a map from f of C prime to G of C, Well, there are two ways to do it. We can either go from f of c prime to g of c prime, and then pre-compose it with the map from f of c to f of c prime, or we can start with the map from g of c to g of c prime. I mean, we can start with the map from f of c to g of c, and we can post-compose it. And it says that the resulting two diagonal morphisms have to be equal, which is precisely the definition of a natural transformation. All right, sorry, yeah, you should be ready to correct me if I make no sense, because it's quite early here. I haven't woken up yet. So we are now ready to formulate our theorem about the computation of Kahn extensions via ends and coends. So recall that the left Kahn extension is a map which extends f along k, and then if some technical conditions hold, if some smallness condition hold plus the codomain category is co-complete, then we can compute left Kahn extension by the formula D is mapping to the coend for all C inside C. And here we take mapping sets from KC to D, and we take copower with f of C, where this dot means that we take the union of f of C d of kc d times. So this is called copower. Alternatively, we can try to compute right Kahn extension, and we will get a similar formula, but guess what? Instead of coend, we will have an end. And now instead of this copower, we will have power. So we write the same thing, FC, but now it is powered with the mapping set. This is power. So it's like a product. So what is happening here is that we have a bifunctor. It's covariant in one variable and it's contravariant in other. So we can take the coend, and the coend computes the left Kahn extension for us. There is a different formula to compute the left Kahn extension, which is not immediately clear or obvious to be the same thing, but nonetheless, it is true that the left Kahn extension can also be computed as a colimit of a diagram which looks like this. We get over category of K over D. We can project it back to C, and we can then map via F to E. We will not talk too much about this formula today, so I guess we will just move on. And going back to the example of the induction, recall that we had G vector spaces, and they were restricted to H vector spaces. By the way, when do we finish? Like, how much time do I have?
50 minutes.
50?
Yeah.
So,
Yeah.
okay, great. So we have induction, which was left CAN extension along our inclusion. So BH was including into BG. And so we had this induction, and we now can try to apply our formula to get something meaningful. Let's do it. So we get that induction GH to, so it takes some H vector space and it produces some G vector space. So say we have some space X. This is an H vector space. So its induction is a G representation, which can be computed by taking all, let's look at the formula again. So we take all C in C. Maybe I should write our diagram again. We have F from C to E. We have E from C to D. Here we have our left CAN extension. And so we take a coefficient over all C inside domain category. And we apply F to C's and we co-tensor it with mapping spaces in D. So how does it look here? Well, here we have this F as our, we have X as our F, and we have I as our K. And here we have our induction. So what the formula tells us is that we should take all the objects in the D looping of H. And here we should take all the morphisms in BG from the image from, so I of a star to X. And we should co-power it with the value of our functor F, which is in our case X, on this object. So what does this mean in our case? Well, we have only one object. What is maps in BG? Here is not X, sorry, it's another point because we computed. So this is a functor, again, it's computable on the only point of BG. So what is this mapping set? This mapping set is, of course, just G. So we get G co-powered with X. And so this is some union of X's over all G in capital G. But there is a twist, which is, of course, added by the fact that we take the coefficient. And what does the coin tell us? It tells us that, well, we can take x enumerated by g, and we can either re-enumerate it by saying that now it's indexed by gh, or we can just apply h to it. And the coin tells us that this has to be equalized. So induction GHX. So we again get something tensor product-ish. We get that GV, where V is some vector inside X. We get all kinds of GV. But there is the relation which says that GH of V lies in the same class as G and H of V. We should say that we factor this set by this, and this wonderful construction is our induction. Now, since we can take all h's to the right or to the left, this is just the same as, let's write it here on the left. So induction of X turns out to be the union of X's, but they are enumerated not by G's, but by elements of this coset G over H. Yeah. Any questions here? So it's like, yeah, it is the set of GV over this relation GHV equals GHV.
Is it the same as tensor product of G and G module V over submodule over
sorry, a tensor product of G over G module. What?
I mean an analogy in group theory. We can or model theory modules. We can take two G modules and form a tensor product over if we have, for example, if we have a group G and subgroup H, we can consider group algebra Z G and multiplied by some G module tensorial over ZH module.
Mm.
And this construction looks like this one.
Yeah, I'm pretty sure you can express this one as a extension as well. But here, the groups are not assumed to be abelian, so not sure how you speak about tensor products here. You have really to specify what kinds of call sets you are taking left or right, for example. It is important, and so it's a bit more rigid, I would say. But yeah, the analogy is of course direct here. Of course, you can express inductions and co-inductions not only in vector spaces but in arbitrary categories. And modules. What are modules? Well, modules are also like one object categories, so nothing stops you from also writing out CAN extensions. I'm not sure exactly, but I think something should be possible here if you want to express this as a CAN extension.
Thank you.
Okay. Any other questions or comments? Cool. Now, another example I wanted to mention is related to what has been to some extent covered last quarter here on this seminar. That is, there was a series of lectures devoted to the model category structure on spectra. And I must confess, I'm not sure how this whole story ended, but I think what you did not really cover is the next step in constructing stable homotopy theory, which is introducing symmetric monoidal product on spectra. And well, this is very tricky, and people have shown some inhuman wit and creativity in their pursuit of this good smash product. But it turns out that there is some conceptual way to see it, at least in the case of orthogonal spectra and symmetric spectra. And that is, we can say that our spectra are some diagrams, and then their product, their smash product, can be seen as a Day convolution. So let us assume that we have this triangle, and now instead of C we have C times C, and instead of D we have just C. And so C and E are assumed to be monoidal categories. And then we can extend it by left CAN extension to produce something which goes from, I mean, we can compute them pairwise. So we can take N and B, we can form their tensor product, C, or we can send A and B to f of A times G of B. So we're assuming that we have two functors, f and G from C to E. Then we would like to somehow get f1 functor from C, not from C squared. And the natural thing here is to try to take the left CAN extension. And I also thought, right now, what if we take right CAN extension? I'm not sure why it is the left CAN extension that gives us something meaningful. If somebody knows, you can tell us. But anyway, we can form this left CAN extension, and this is called the Day convolution of f and G. It's probably denoted as f tensor day G. And given that we know how to compute left CAN extensions, if E is co-complete, we can write that what F convoluted with G does with some C is it takes this wonderful coend. So we take all the pairs in C and we take C sets from the product of C1, C2 to C, and we co-power it with F of C1 tensored with G of C2. Yeah, because this is our form sets from the formula, and this is our functor. This is our functor, which was denoted by F previously. Yeah, now, for example, symmetric spectra is some modules inside some in some category of topologically enriched category from some funny category into some compactly generated topological spaces. And so this gives us a chance to introduce symmetric monoidal structure, symmetric monoidal category structure. On symmetric spectra. And if you take this formula and you write unraveled definitions for some spectra and their identifications with functors, then you will get your usual formula for the smash product between symmetric spectra. And you might expect that because this formula introduces some factoring with respect to the action of the group sigma of permutations. And of course, this will be precisely the factoring which coens tells us to perform. Yeah, and finally, maybe I should say by modules. Well, because in spectra we have these connecting maps. We have S1 smash xn go into xn plus 1. And so you could see where module structure comes from. This smashing with S and going back to X after smashing with S is what you get if you unravel a definition of an S module structure. So symmetric spectra has 0 modules inside some functor category. You can also pass to orthogonal spectra this way, and you will get your usual formula for the smash product between orthogonal spectra. You can also see here immediately why for sequential spectra this is not going to produce a symmetric smash product. All right, another example is taking place if we try to extend some functor along identity. So we expect that extending along identity is not going to change much. So the left-hand extension of F along identity is nothing but F itself. But we can write it via our coend formula, and this will tell us that f of c equals to left Kan extension of f along 1 of c, and this will be, in our case, c of d, no, d. Now, I have reserved the letter c quite unfortunately, so it will be c of d, c, f of d. So we get this funny formula that f of c is equal to this integral, which can be called the Dirac formula because it looks precisely like the Dirac formula from quantum mechanics or functional analysis. This is called the Koyone dilemma. Yeah, also note that what is figuring here is representables. So what this formula shows us, in addition to everything else, is that every functor is the colimit of representables. It's also known as density theorem. All right, and I promised to show why skeleton is indeed the skeleton. So recall that we had simplicial sets restricting to simplicial, like to truncated simplicial sets. And we had left Kan extension here. And the comonad corresponding to this adjunction is the skeleton functor. All right, let's write the formula. Skeleton is this left Kan junction of inclusion of this truncated simplicial category inside in the whole simplicial category, say I, of restriction of X. Let's call this restriction Y. Then expanding the formula gives us that we should take coend over which category in this case? Well, restriction is like pre-shifts on this truncated guy. So this is for all, say, K inside the truncated simplicial category. Here, what we write is simplicial category opposite because these are functors from the opposite category. Now from K, okay, we should introduce some variable which we are, some object which we are taking the value on, say M. So it's opposite Km times X K. Not xk, but yk. Now, what is this thing? This is the same as simplified category from M to K. And now, if we assume that M is greater than K, and assume that M is greater than N, then we would like to show that all these M simplices are degenerate, because this is what we expect in the N skeleton, right? We get rid of all non-degenerate high simplices. So let's see. If M is greater than N, then this map from M to K is an epimorphism. Moreover, it factors as an epimorphism on some M prime followed by an inclusion. And this epimorphism has to be some composition of degeneracy. So it's not just an epimorphism, it's a degenerate map. But this means that this summon here is actually coming from Km prime yk. And there is degeneracy map here. Which makes us conclude that all M simplices are degenerate because they are coming from, by degenerate map, they are coming from some other simplices. So this was the first part. And also, we can have that M is not greater than N. But in this case, let's look at this coend again. So M is not greater than N. Then I'm claiming that this is just the same as just ym, because when m is not greater than m, then we can, well, be at least a bit hand wavy here, but the point is that we take k, which are not greater than n, and m is not greater than n, so we can reduce all this to those k where k is not greater than m. But in this case, this is just the Koyana dilemma. And so we conclude that the skeleton n of x is just obtained by discarding all non-degenerate simplices of dimension higher than n. Cool. Any questions here? All right, let's move on. So this claim that all the Khan extensions that arise, quote unquote, naturally in real life are actually not just Khan extensions, but the pointwise Khan extensions. And a general Khan extension is not really well behaved. So say that a functor f preserves a left Khan extension. So, okay, f is reserved by what we have been using here. So let's go with the function g. And if we have some function to some, say, e prime, and we have the left Khan extension of f over along k, then what we can do is we can compose g with this left Khan extension, and we can whisker our natural transformation to get this natural transformation from g composed with f to g composed with left Khan extension, and then with k. And if the result of this composing is giving us the left Khan extension, then we say that g preserves the left Khan extension. So if g composed with ln kf, and let's denote it by some letter. So if this pair, this functor, and this natural transformation is a left Khan extension of the composition of G and F. Along K. Now we say that I don't know what this was. All right, so let's say we have right Khan extension. We say that this Khan extension K is pointwise. If it is preserved by representables. So what is happening here is that we are taking functors to set which have this particular form, and we ask the functor, we ask the Khan extension to be preserved by it, and then if it agrees to that, we say that it is a pointwise Khan extension. And it turns out that these are precisely the Khan extensions which can be computed by the formula which I was giving when I was after I was introducing covariance and ends. I mean the second one. So the right Khan extension of f along k is pointwise. If and only if it can be computed as then you can, oh, amazing. So if you have a functor, you can map C into the terminal category. And what is the left Khan extension of this thing? Well, of course, this is the co-limit over C of f. I guess the easiest way to see it is just via the universal property. You can also see it by taking the covariant formula. You can also see it by taking the second formula. And probably you can invent a couple of other ways to prove it. So now that we have this functional transformation from f to something which factors through the terminal object. So this is precisely the cone. And the universal property tells us that this is the limiting cone. Okay, we can write this. So we have technical issues. Okay, so we have maps from the star from this left Khan adjoint, left Khan extension to some other, say, object X. Is the same as maps of maps from F to X composed with this map with interterminal object, but this is precisely the cone on X. So it tells us that left Khan extension represents maps from F into cones, and yeah, this is just the definition of co-limit. Now, for another illustration, assume that we have an adjunction. Then we have its unit. One to GF, its unit. And guess what? This unit is precisely the unit for the corresponding Khan extension. So we have GF, we have this unit, and G is the left Khan extension of unit along F. Now, this is not as trivial as the previous example. Somehow it is actually not immediate at all, I would say. It's left as an exercise in drill. I guess you can find it in MacLean, if I remember correctly. It requires a bit of trickery here, But nonetheless, the moral is that you can express both limits, chemical limits, as well as adjunctions as Kahn extensions. Now we have already seen the Yoneda lemma. Here, we've seen the co-Yoneda lemma, and the Yoneda lemma comes from, of course, considering ends. So it will be a right Kahn extension. I actually don't remember, but probably it has to be F, C, and probably we take the right Kahn extension. Is it true? So if we take this, yes, so we write this right Kahn extension on some D, and this is this coend. And we've already seen that this is natural transformations. This is natural transformations from representable represented by D into F. And this is our example that you can write natural transformations as an end. Yeah, and of course, this right Kahn extension is equal to F of D, so we get our co-Yoneda lemma. Not co-Yoneda, but just Yoneda lemma. All right, and the final example. Let's kill all this. And write this again. So assume that now we have some category E, and we are mapping. So this is what used to be F. We are mapping via some map delta, which we are not specifying. And there is a Yoneda embedding of the simplicial category inside simplicial sets. And we can consider the left Kahn extension of it. So what is the left Kahn extension of some X? Yeah. So we take left Kahn extension along this Yoneda embedding. What we get is we power this thing, so we go over all n inside simplicial category, and we embed them via Yoneda. yeah, we should actually write some x. So yeah, so this value on some simplicial set x is this coend. Now the first multiple here is of course just xn. So we get the coend xn co-powered with this delta n. And of course, if you take now E to be topological spaces and this delta functor to be the evident functor, which just takes n into the simplex on n+1 vertices, then you get the standard geometric realization of a simplicial set. And in general, this is called the geometric realization. Of course, we have to assume that E is co-complete in order to apply this formula. All right, any questions here or in general, comments? This is all I had to say.
And here we have a Cartesian multiplication in the integral term n multiplied by delta n. In the construction of geometric realization, we have a push out of Cartesian products, yes, and this is the same thing, yes.
This is just so we can recall our diagram for the coend. This will be union of delta n over xn, and we co-equalize it with respect to arrows, to two arrows. So our geometric realization is the co-equalizer of this. So this is like some n and x quotient over, okay, then I should put this bracket here, quotient over and phi x equals and phi x. So you can take coordinate on a simplex, or you can either include it geometrically into some other simplex via some Fraser degeneracy map, or you can reindex it abstractly, and this has to be glued together.
Yes, but in this context of coend, what is the relation between them?
How this is equal to this?
Yes.
So this is like a functor. So the definition of the coend was let's jump back to the definition of the coend. Oops. All right, so here we said that the coend is this coequalizer. And in our case, we have h of n m equaling x n times delta m. And this equals to, well, yeah, this equals to union of delta m's over xn's.
Okay. What is an intuition of end and coend informally?
That's a good question. I think that the tensor product is the best intuition. This is why I've included this example, because, well, here it's quite evident what is happening. You just apply this tensor product relation. Sorry, wait a second. Right, so we have this tensor product relation. So if your h factors as a product, which is the case for realization, by the way, then you get this tensor product-ish like relation. And I guess this is one intuition for the coend. And for the end, I'm not sure there's some clear intuition. I even saw some mass stack exchange question recently about this. The answer was that there is no intuition, but I guess this example here again is the first one that I've given, that natural transformations can be seen as an end. But okay, for an end it's tricky, but for the coend it's like a tensor product. I guess in shifting geometry and logic, McLean speaks about basically this thing, and he just calls it precisely the tensor product of functors. And in all the examples, almost all the examples that we see, we get relation akin to what's written here, that you can either pull back along some arrow or you can push forward along this very same arrow, and the result has to be coequalized. So I guess this is what you are to keep in mind here.
Thank you. Other questions? Okay, thanks a lot, Arseny.
Thank you.